This is 1.3, linear inequalities in graphs. And so up to this point, everything we've been dealing with has been an equality. And you know about equalities. 2x plus 5 equals 13. And this is an equality. It's an equation. And so to solve this, there are certain moves that you make, certain principles that you apply. These cancel and you get x equals 4 and everybody's happy, right? And so this is a solution to the equality. And if you were to graph this solution on a number line, you would put a tick at 4 and you'd put a solitary dot at 4. That's the solution, x equals 4. That's what makes this true. Let's change it. So 2x plus 5 is greater than 13. And this is an inequality. There are 4 types of inequalities: greater than, or equal to, less than, or equal to. Let's go through and apply, just like we did to the equation, the addition principle and the multiplication principles of equality to our inequality. So this is subtract 5. So you're going to get 2x is greater than 8. And then you're going to divide by 2, and you'll get x is greater than 4. And you're going to put this on a number line. Again, always put a 0 on your number line. A 0 is kind of like north on a map. You always want to know which way is north, and so you always want to have a 0 on your number line. And then we'll put a tick at 4. And now we need the answers that are greater than 4. All the numbers. So what are some examples of numbers that are greater than 4? 5, 6, 7, and you get it, right? Like it's going to keep on going. And so all of these numbers here, we're going to kind of shade this part here. But what about 4 itself? Is 4 part of the solution? No, 4 is not part of the solution because 4 is not greater than 4, it's equal to 4, okay? And so because of that, we can't fill in the 4 with a solid dot. We have to use something called an open dot. If you have greater than or less than, when it comes to the graph, you use an open dot. If you have greater than or equal to, less than or equal to, you represent those with a closed dot, which means we just take this dot and we fill it in. Okay, but that's not the case that we have here, so we're just going to put an open dot there, and then we kind of just shade to the right because it's greater than, right? We want numbers that are greater than 4, and so we shade to the right. How do we know if this is right? How do we know if this region that we shaded, the yellow highlighted region, is correct? So if we've done this correct, everything in green, every number in green should give us a true value. And every number that we pick in red, if we highlight the red region, should give us a false. That's really what we're doing. We're taking the number line and we're making 2 camps. The green camp, which makes the inequality true, and the maroon, purple, fuchsia camp that makes everything false. So if you pick a number over here in the green camp, 5, and you plug it in, it should make this true. So is 2 times 5 plus 5 greater than 13? Yep, so it makes it true, so everybody's happy over here. This is the true region. Okay, great. Now let's pick something in the false region. And if we pick it, we should be able to plug it in, and it will make a false statement. So what number do you want to pick in the false region? 0 is an excellent, and really you could pick any number in the false region, but 0 is awesome. Why is 0 awesome? Because it's easy to calculate, right? You plug it in, it knocks out a whole bunch of stuff. So plug 0 in, and you get 5 is greater than 13. No, false. So 0 and all his buddies on this side make it false, and we don't care about those. Those are not part of the solution. So we know we've done this correctly, because when we pick test points for our hypothetical solutions, they make it true. All right, let's do another one. So now we've got negative 2x plus 5 is greater than or equal to negative 13. So again, doing the same thing that I did before, I'm going to subtract 5 from both sides. Subtract 5. This cancels. I'm going to get negative 2x is greater than or equal to negative 18. I'm going to divide both sides by negative 2, and I get x. These negative 2's cancel. X is greater than or equal to negative 18 divided by negative 2 is positive 9. So x is greater than or equal to positive 9. Draw a number line. ticket 0, ticket 9, open dot or closed dot at 9. Arrow should go to the right. Right? According to everything we've learned so far, all the stuff that we're familiar with, we're like, this is what should happen, right? We've done nothing wrong up top. So this means that these points should make our inequality true, and these points should make our inequality false, according to what we've done so far. And so now we pick some points. And again, we'll pick, to make a true, for the case for true, we're going to pick 10. So we should be able to take 10, plug it into this guy, and it should make it true, right? So we do that. Negative 2 times 10 plus 5 is greater than or equal to negative 13. So you get negative 20 plus 5, and what you end up with on this side is negative 15 is greater than negative 13. True or false? False. But it's supposed to be true. This is a point from our true region. Why is it giving us a false reading? Then we pick one from the false side, 0. And 0, remember, should give us a false. It should not be true. It should be false. So when we take 0 and plug it in here, we get 5 is greater than or equal to negative 13. That should be false. But it's not false. It's true. So something's really goofy when we take the strategy that we've used for the other two, plugged it in, and tried to verify our regions. Our false regions are giving us trues, and our true regions are giving us falses. So how do we fix that? We fix it by, instead of shading this part green, we shade this part green. And instead of shading this part purple, we're going to shade this part purple. So now our graph, the shading of our graph, matches the reality of plugging points in, okay? The arrow is now over the false region, and we don't want the arrow to go over the false region. We want the arrow to go over the true region. So that means we've got to switch our arrow. Well, if we switch our arrow, that means instead of graphing greater than, we have to graph less than. So that means we have to change this sign. And what was the stimulus that made that happen? Dividing by the negative 2. So the rule is, new rule, we got to change our rules. The rule is anytime you multiply or divide an inequality by a negative, you have to flip your inequality symbol. Solve the inequality, write the answer as an inequality, and graph it as a solution side. Negative y plus 15 is greater than or equal to y plus 13. What do you want to try to do? Yeah, collect all the y's on one side, get the numbers on the other side, get y by itself. And so let's do that. Now you'll notice this answer looks a little bit different than the other answers that we had because my variable is on the right side, not the left side. So some students really like their variables on the left. They're like, just put the letters on the left all the time. And so if we decide to change this one, again, we're dealing with an inequality, not an equality. So you have to pay attention to the sign. When you flip this one around, you're going to get y is less than or equal to 1. So we're going to say y is less than, oh, and this is how you write less than or equal to. You do the less than symbol, and then the equal symbol, and then the number 1. That's how the computer system recognizes it, because there's not a less than or equal to 1 or less than or equal to symbol on your keyboard. What does the graph look like? Closed dot or open dot? Closed dot at positive 1, and then arrow to the left or arrow to the right? Arrow to the left. How would you write this in interval notation? Parenthesis, negative infinity, comma 1, and you can call it a square bracket. Some people call it a hard bracket. Either way. So when you had, remember back up here, oh, I erased it, greater than or less than, we said that was an open dot on the graph. Those are associated with parentheses. If you have a greater than or equal to, less than or equal to, those were closed dots. And those are associated, when you write that symbolically, as hard brackets or square brackets. Okay? So when you're writing things in interval notation, you have to use the parenthesis bracket notation. In this case, we have a parenthesis, an open dot at negative infinity. Why is there an open dot at infinities? Parentheses, and then dot, 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 infinity symbol. See how I did that? So this is one way you can remember infinity symbol always has parentheses on it. Whether it's negative infinity or positive infinity, doesn't matter. Always has parentheses. Closed dots have the hard bracket. And you'll get used to this because we're going to use interval notation a lot. 6 less than 4x minus 6 less than 14. Okay, so let's add 6 to all three sides. Add 6, add 6, add 6. Divide everything by 4. As a note, if we were to divide everything by negative 4, we would have to flip both inequality symbols. How would you graph this? Let's start with dots. We know we're going to have dots at 3 and 5. Open dots or closed dots? Open dot. So we're going to have an open dot at 3. Boink. Open dot at 5. Yeah, everything in between 3 and 5, right? So you're going to kind of shade like this stuff right here. How would you write the solution in interval notation? This is always the lower number, and this is always the upper bound, your upper number. It's like an ordered pair. So you always write the lower bound first, comma, and then the upper bound. And so the lower bound is 3. That's the left-hand side, the left-hand boundary of our solution. And 5 is the right-hand side. That's the upper bound of the solution. So it's parenthesis 3 comma 5. And we're going to do this one in 2 chunks. Here's one part. So we're going to solve that. And here's another part. So here we go. 10x plus 9 is less than 5x plus 29. X is less than 4. So that is the yellow solution. All right, so I got x is less than 4, and x is greater than or equal to 1. So let's graph these. So I'll put a tick at 0, a tick at 1, and a tick at 4. Tell me about the yellow graph. Open dot and shading to the left. Tell me about the blue graph. Closed dot and arrow to the right. There was a word, and. What region contains the solution? Between 1 and 4. And what color region is that? Green. What do yellow and blue make? Green. Get it? See, like we work on multiple levels. The yellow is everything less than 4. The blue is everything greater than 1. And because we're using the word and, that means we want to know what points make the yellow true and also simultaneously make the blue region true. So if we were to write this in what's called set notation, you would write something like 1 is less than x, or pardon me, less than or equal to x, which is less than 4. So this is how you'd write it in what's called set notation. We're not going to use set notation. Instead, we would like to write our answer in interval notation. Close dot at 1, so hard bracket, 1 comma 4. That's your lower bound, your upper bound, left-hand side, right-hand side. And then a parenthesis on the 4 because it's an open dot. Is that good? What if we change the word from and to the word or? You're looking for the solutions that make one true or the other one true. Not both at the same time, simultaneously, but either the yellow graph is true or the blue graph is true. What would that solution be? So this is a what if. This is kind of an extension. What if we said or? What would the solution be for, this is the solution for and, right? What would be the solution for or? Everything's a solution in this problem for the or. What numbers make one or the other? What numbers make the yellow one true or the blue one true? Every number does, right? Like you pick a number in the yellow region, it's a yellow, because they overlap, right? Where this or situation gets a little bit more squirrely is if we had a graph that looked like this. Zip, zip. Now you would have a gap, right? And so if you were to or this, if we called this A and we called this B, you would say the solutions are negative infinity up to A and then B up to positive infinity. Because there's a gap of solutions that are not satisfying one or the other. These are solutions in one dimension. It's a number line. A number line is a one-dimensional, a line is a one-dimensional thing. And we also know it's one dimension because there is just one variable, x. Well, what if we got creative and went to 2 dimensions? So now we give you 2 variables, an x and a y. So now instead of solving this on a number line, we now solve it in a two-dimensional plane. Don't worry, we're not going to do 3 dimensions. Your brain would melt. What do you want to do with this?
Get y alone.
Yeah, let's get y by itself, right? I mean, that's what we would do if this was an equal sign, right? You would just, and we would apply all the same rules, and right, so this maybe is kind of familiar. So we're going to say 4y is less than or equal to 8x minus 20. So if you move stuff around and manipulate the equation, you're going to get y is less than or equal to 2x minus 5. And this looks like something, right? You can read this equation. You're like, oh, your y-intercept's -5, your slope's going to be 2. Remember when we were back in one dimension, we talked about 2 things we had to determine with our solution. First, we had to determine open dot, closed dot. And then we had to determine, do we shade to the left or do we shade to the right? We got to determine those same 2 things here. So is this an open dot or a closed dot? It's a closed dot, okay? So here's the notation. If you have greater than or less than, in 1 dimension we said this was an open dot. In 2 dimensions, it is a dotted line. So if this symbol in our equation, or in our inequality, was just less than, we would draw a line that looks like this. That means open dot. If we have greater than or equal to, less than or equal to, in the 1D world, it was a closed dot. In the 2D world, it is a solid line. So the first thing you have to do is choose what style of line you're going to draw. And in the homework, there's a button down at the bottom that says draw a solid line or draw a dotted line. You got to make sure you pick the right line. So we have a solid line in this situation. Great, so here's our line. Now we have to determine, do we shade above that line or do we shade below that line? Do we shade to the left or do we shade to the right, kind of is the idea. And there's a little bit of a shortcut we can take here. The shortcut is, if you have y by itself on the left-hand side, y is on the left, and the symbol is less than, then you shade below the line. Less than means shade below. So that means we're going to shade all this stuff. And that means every point in the green region, every xy coordinate, is a solution to that inequality. So this is the true. These are the true camp, and this would be the false camp. And we're only going to shade the true points. And at this point, we could do that whole pick a point and try it, right? And test out, pick a coordinate over here in the green zone. How about a nice coordinate like this one? This is 10, 2. So that means you're going to put a 10 in for x and a 2 in for y. And if you do that, you should get a true statement. Let's try it. -80 plus 8 is less than or equal to -20. Is -72 less than or equal to -20? Yep, it is, so that's true. You could also prove by counterexample. Let's pick a point in the false region and verify that it makes it false. And what point that is totally awesome that you want to pick in the false region? 0, 0, excellent. So you're gone, you're gone. 0 is less than or equal to -20. Is 0 less than -20? Nope, it's greater than. So 0 gives us a false like we anticipate, and the point that we picked 10, 2 gives us a true. So look at that, we just did this in 2 dimensions.